welcome to CEC lectures. Myself Dr. Preeti Jagwani from Department of Computer Science, Aryabhat College, University of Delhi. So we have started with our topic of indexing and hashing, and we have also covered one lecture about the indexing, in which we have seen what is actually the concept of indexing, and we have also seen the type of one particular type of indexing, which is ordered indices. Now covering starting from there only and going further, if we talk about the ordered indices, you have seen that ordered indices can be clustered, or it can be non-clustered, and in clustered we are going to kind of maintain an index in structure in which we are going to have search key and the corresponding pointers which are pointing towards the records. Now when we talk about the types of ordered indices, we have two types of ordered indices. One is the dense index and another one is the sparse index. These are the two types of ordered indices. We will be soon covering this dense index and sparse index, but before going to the types of ordering indices, what we need to cover is hashing, or we can say hash indices, which is basically the type of indexing. So in ordered indexing, I have told you that we are going to have a particular sequence of search key, while in hashing we are going to have a distribution of the keys in a or records, we can say, in a particular bucket. So let us begin with hashing. So why do we need kind of hashing is let us consider the scenario in which there is kind of we have a particular relation which is kind of huge, and we have and that is a sequential file organization. We have also maintained and ordered indexes of this particular sequential file. So one disadvantage of the sequential file organization is that we must access the index structure in order to locate the data. Now in order to access the index structure, we can use kind of binary search. Now binary search, as you are aware, is exactly going to discard half of the data at a particular time. So this is going to result in more input output operations, and this is something which we actually want to avoid. That is, more input output activity is something which is not desirable for a fast access. Now if we have instead of this ordered index, or instead of the sequential file organization and the corresponding index, if we have the file organization which is based on the technique of hashing, that is going to allow us to avoid accessing an index structure. And hashing also provides a way of constructing the indices, and as we have constructed the indices, we can also kind of access the particular record. Now when we talk about hashing, we have 2-3 terms which are really important here. One of them is the bucket. So bucket, as I have told you in the previous lecture also, that bucket is, you can say, kind of storage area. So bucket, here we will be using the term bucket to denote a unit of storage that can store either one record or more than one record. Generally we will talk about the bucket storage as more than one records, and bucket is typically taken as a disk block, one complete disk block, but could be chosen to be smaller or larger than a disk block. There is no constraint that a bucket is always will always be equals to one particular disk block. It can be smaller than a disk block or it can be larger than a disk block, and that depends upon the we can say requirement of the application. Now here we have one terminology which is also called hash function. Now in order to understand the term hash function, let us say that the term k denotes the set of all search key values, and b denotes the set of bucket address. Now basically what we want that on taking the k, which is a search key value, we need the term B, or we need the bucket address B. We will be taking K and we need the bucket address B. So, hash function is a function which is going to translate, or which is going to transform the value of K to B, or simply we can say a hash function H is a function from K to B. Let us denote this hash function as H, and to insert a record with search key, or in order to access the record with a search key K of I, we need to compute H of K of I, which is hash function of hash of K of I, we can say, and this H of K of I is going to give us the address of the bucket for that particular record. So, for example, I am just giving a very kind of very small, a very layman example. Let us say the search key is 1 2 3. So, 1 2 3, so 1 plus 2 plus 3 could be is 6. So, this could be in the bucket number 6. So, some kind of transformation, some kind of function we are going to apply on this search key, which is denoted as a hash function, and to access that to access the record with that particular search key, we are going to compute that H of key Ki, and this H of Ki is going to give us the address of the bucket for that particular record. Now, let us understand it more clearly. In order to perform a lookup on a search key value, let us say key Ki, we simply compute H of Ki as I have just told you, and then search the bucket with that particular address. Now, let us say we have two search keys, one is K of 5 and another one is K of 7, and they have the same hash value, which is H of K of 5 is equals to H of K of 7. Now, in order to perform a lookup on K of 5, the bucket H of K of 5 must contain record with search key values K of 5 and the records with search key values K of 7, because I have told you that H of K of 5 and H of K of 7 is same. Now, then further we will be checking the search key value of every record in the bucket to verify or to look for the record which we are actually looking for. So, that is something when we talk about a lookup. Now, let us say we are looking for a deletion. So, if you say deletion, just imagine that deletion is also kind of looking for the bucket first and then deleting the record, because first we need to reach on to the location and then we will be kind of deleting the record from the bucket. So, if a search key value of the record is to be deleted, let us say that is key I, we compute H of key I, and then we will search the corresponding bucket for that particular record, and that bucket address is being generated from applying the hash function H on key of I, and then we will be deleting after getting access, or after reaching or after locating that particular bucket, we will look for the record and then we will delete the record from the bucket. So, this is what we can say is the basic idea of hashing. Now, hashing can be used for two different purposes. One is in hash file organization, to obtain the address of the disk block which is containing the desired record which we are looking for. That can be done directly by computing a function on the search key value of the record. This is what just we have seen. And in a hash index organization, we organize the search keys with their associated pointers into a hash file structure. So, this could be a hash file organization, or this could be a hash we can say a hash index organization. Both are valid in both techniques we can use in databases. Now, coming to initially we have seen what are indices, why do we need indices, we have established the platform, and then we have seen ordered indices in the previous lecture, and in this lecture we have seen hash indices also. And in the starting or in the beginning of this lecture, if you remember, we have seen two types of ordered indices. One is the dense index and another one is the sparse index. So, in order to make the discussion of the ordered indices complete, let us begin with the types of ordered indices, that is the that is the dense index and the sparse index. So, in dense, let us take dense index first. So, in dense index, an index entry appears for every search key value in the file. As we have seen the example earlier, that was the example of a dense index. As you can see on the screen, the search key value here is the faculty ID, which is the first field in our relation. Now, that particular complete field is taken as the search key of the index structure, and for every search key we have a pointer which is pointing towards the original, or which is pointing towards the record in the database file. So, what is happening here? Each and every employee ID is having a corresponding entry in the index structure also. This is what you call when we maintain our ordered indices in such a way, this is what you call we can say a dense index. So, basically in dense index, an index entry appears for every search key value in the file, as we have just seen, and in a dense clustering index, the index record contains the search key value and the pointer to the first data record with that search key value. Now, why I am saying the first data record, we will be covering the concept of collision in the hash indices, and then I will explain this concept. Now, if the rest of the records with the same search key value would be stored sequentially after the first record. Now, what is the example here? So, for example, let us say my search key is department. Now, obviously, it is not going to be there that only one faculty is there in one particular department. There will be multiple faculties. So, that concept comes in here, that the rest of the records with the same search key value would be stored sequentially after the first record, but the index entry of physics will be pointing towards the first record of the instructor from the physics department. Other entries of the physics department will follow that particular record, because the index is the clustering one, and we have earlier seen that what is a clustering index. The records are stored on the same search key. And also, if we talk about a non-clustering index which is of type dense, the index must store a list of pointers to all the records with the same search key value. So, either it is a kind of clustering index, or it is a non-clustering index. Both can be maintained with the help of we can say dense indexing, and here is the example of the dense indexing, that each and every we can say each and every value of the attribute is appearing in the search index also, and corresponding pointers are being pointed, corresponding pointers are pointing towards the records. Apart from dense index, the other type was the sparse index. So, sparse index, as you can see on the figure, this is the example of sparse index. So, in the sparse index, please notice that we have the search key of employee ID or faculty ID, that means the same search key which we have taken in the example of dense index. But here the index is itself is not containing all the values of the search key. Why? Because this is a sparse index. So, for example, someone is looking for 101001, then it will be directly pointing towards this. Now, let us say someone is looking for 15151. So, the next entry in the index is 32343, and please remember that these are in the sorted order. That means the previous link of 10101 is to be followed, and then other entries, or the other entries which are stored after that particular record of 10101 are needed to be looked upon. So 10101 not satisfied, that means we are not looking for this. The next one 12121, we are not looking for this. Then 15151, yes, we are looking for this. But here the index itself is not maintaining all the values of the search key, and hence your index or the space overhead of the index is, you know, kind of we can say is less as compared to your the dense ones. So in sparse index, an index entry appears only for some of the search key values, not for the all search key values as we did in the dense index. Also, sparse indexes can be used only if the relation is stored in the sorted order of the search key, that is, if the index is a clustering index. Then only we will be able to use the sparse indices. Otherwise, having the sparse index in a non-clustering index situation is just not possible. Here you can see on the screen that the in a search key, which is our faculty ID here, is in the sorted form. If would not have been in the sorted form, then it is not possible to have a sparse index of this. So if the search key is not in the sorted form, that means your index is actually a non-clustering index, and for non-clustering index it is not possible to have a sparse index entry. Also, in the case of dense indices, each index entry contains a search key value and a pointer to the first data record with that search key that we have already seen. Now, in order to locate a record, we need to find the index entry with the largest search key value. This is what I am talking about hash, this is what I am talking about the sparse indices. In order to locate a record, we need to find the index entry with the largest search key value, that is less than or equals to the search key value which is being searched, and we need to start the record pointed to by that particular index entry and follow the pointers in the file until we find the desired record. Let us take this with the help of an example. So, for example, if you are looking for something which is 76543, so we will be looking for the entry in the indexes. We have 32343, and after this 32343 we have 76766. So 76766 is actually, we can say greater than the search key which we are looking for, because we are looking for 76543. So we will be following the pointer of 32343. So following the pointer of 32343, you have, on the right side of the figure, please notice that there are arrows from one particular record to another, and these arrows which are shown there are actually indicating presence of a linked list there, in which one particular previous record is linked to the another one. So 32343, or having the pointer to 32343, it is easy to go to the next record, which is 33456, because the pointer is there. Then it is easy to hold on 455665, and then after that we will go to something in 58583, and then we will be jumping to the 76543, which is the which is our desired record. So in this way, so first we will be finding the index entry with the largest search key value, that is less than or equals to the search key. So if we are looking for the search key of 76543 less than or equals to entry in the index is 32343, and following the pointer of 32343 and then following the pointers which are stored in your actual relation, we will be we will be ultimately looking for 76543, or we will be ultimately landing for 76543. So, for example, we are talking about an entry. Let us take one more example. We are talking about an entry 222, So, 222, we don't have in this sparse index, if you can see, and the last entry which is less than or equals to this is the first one, which is 10101. So, we will be taking 10101, and we will be then following the pointers and looking for our own entry, and if we kind of end up with the next index pointer, we do not have that and we are not able to find the record, that means the record is not available, because all the records here and your index itself are sorted also. And then here in this way we can go to this particular record which we are looking for. Now here if you can see on the screen, we have one more example of this sparse index. Now this index is not according to the we can say our faculty ID, but the search key here is the subject, and please notice the relation, the actual relation. All the records are being stored in the sorted order of the subject, which is biology, followed by computer science, then electrical engineering, then finance, then history, then music, and then physics. So, this is a sorted list of instructors according to their subject, and the sparse index here is containing this particular search key of subjects. So, it is having it is having pointers pointing towards the record in biology, then pointing towards the first record in computer science, only the first one, because the rest will be followed. Then we have one record pointing towards the electrical engineering. Then for the 2 records of finance we have only one pointer, for 2 of history we have one pointer, and for music, and then for 2 of physics we have one pointer. So, for example, we are looking for one particular kind of we can say brand, the instructor brand, which is who is in computer science. So, we will be following the pointers of the computer science, and then after within the we can say range, or within the records which are of computer science, we will be looking for all the instructors which are there, and ultimately eventually if the instructor is there or the record is there, we will be able to find out our record. So, this is what your we can say sparse indices are. Each and every entry of the search key is not maintained in the index structure itself, as we did in our dense structure. So, we can say if we compare this with a particular book, or we can say maybe a dictionary, the header of each page lists the first word alphabetically on that particular page. So, notice in a dictionary you have the header of each page with having the first word alphabetically, which is on that particular page. The word at the top of each page of the book index together form a sparse index on the contents of the dictionary pages, and please recall that we use this sparse index which is available in a printed dictionary a lot. Also, as we have seen, it is generally faster to locate a record if we have a dense index rather than a sparse index. Yes, because dense index is having all the entries, or that means pointer to all the records. However, sparse indices have their own advantages over dense indices, that is they require less space, because dense index is going to have all the pointers, all the keys, all the values of the search key, then it is obviously going to be large, while the sparse indices are not having all the values of the search key, that means they are occupying less space. So, less space overhead is there, and also they impose less maintenance overhead for insertion and deletions also. So, here in this lecture we have seen hash indices, also we have seen the 2 types of ordered indices, which are sparse indices and the dense indices. Here is a list of references which is being used for the preparation of lecture. Hope you have enjoyed one. I will see you in the next lecture. Till then, take care. Goodbye.